Hello, guys. I hope you're doing great. So today, let me just give a hint and we give a solution, a quick solution on this um, differential equation. So we are going to solve a series of differential equation in this video, okay, with different method and different um, solution or different method, okay, and all of them are just this is a kind of refreshment, okay, for you that is forgetting all the method that we have done. Okay, so I will solve this equation. Some of the equation I will solve twice, okay, with different two methods, and other I will just solve once and I will leave it. Okay, the most important thing here is just for you to understand when to use this method and how to use. Okay, so let's go. Suppose we have this first equation. This is the first equation that we are going to solve. So we have xy plus 1 y dx plus 2 minus xy x dy. So if you see it closely, okay, if you see this well, you will notice that this equation is in the form of f of xy y dx plus, okay, plus f of xy x dy equal to 0. Okay, so this actually is in this form. So now let me first see, okay, why did I why did I realize that is in this form? Because check, okay, see, this is a function of xy only. This is y dx and also, okay. So when you are trying to solve a differential equation, first degree and first order, you have to check which, okay, which case would be like easy to be applied. And in this case, as this function is already drawn in this form, so easily, okay, the first or the second point you have to see is like whether this function is exact or non-exact. I know, okay, just by seeing, I know this. But the first thing I have to see, okay, whether I want to solve, if I want to solve this one, is check whether this function is exact or non-exact, okay? Like making m, okay, m will be this expression right there, and n will be this expression, okay? Okay, just by seeing, I know this, but let's just go in a simple way or in a general way. So here, m, I have m and I have n. So, okay, this is m dx, this is n dy equal to 0. Now see, what you have to do here. We have to check whether this function or whether this equation is exact or non-exact differential equation. Okay? Find del y by del n. Okay, del m by del y and del n by del x. See whether this will be equal or not. This time this xy square derivative, applying derivative, differentiate xy square plus y with respect to y. It will be 2xy plus 1. Now, if you differentiate this guy with respect to 2x, what will it be? 2x minus x squared y. So, it will be 2 minus 2xy. Okay? Surely, it is not, these are different. Okay? If they are different, so it is not exact. Okay? It is non-exact differential equation. Okay, so if it is non-exact differential equation, now comes, okay, now it comes. It is in the form of f of xy, okay, y dx plus f of xy x dy equal to 0. So if it is in this form and it is non-exact, what does it mean? It means that to make this function or to make this equation in a exact differential equation, I have to multiply all this expression or all of this equation by if. And what is the if? Okay, the integrating factor. What is the integrating factor for this case? Okay, for this case, the integrating factor is 1 upon mx minus ny. If you are in doubt, just roll down on this math 2 section of this of the V-Numerical channel, and you will find all about this case, okay? when the function look like this, or when the equation look like this, and blah, blah, blah. Many exercises are solved there in detail, so you can just have more, how can I say? Yeah, you can be more enlightened by watching this video, okay? Now see, this is the integrating factor for this case. So it means that here the integrating factor will be m times x. What is m? M is this time this time this, okay? So m will be xy plus 1 times y, this is normal y, then times x. So I'll get xy minus, what is n? N is 2 minus xy times x, then multiply by y. So times xy. Okay? Now see, this integrating factor can be reduced into xy. This is common factor, xy. So it will be xy plus 1 minus 2 plus xy. So what will it be? It will be xy down here 1 times this, 2xy, and this, minus 1. This will be our integrating factor. So the next point, or the next step is, after finding the integrating factor, I will multiply this integrating factor by all of this expression. Okay? So this will be 1 upon xy, then 2xy minus 1 times xy plus 1, okay, dy, plus 1 upon xy, okay, 1 upon xy, 2xy minus 1, okay, time 2, and here I'm using y, okay, y dx, 2 minus xy, then x dy must be equal to 0. Okay, if you multiply this, you will see that this y and this y will be cancelled out, and this x will be cancelled out. So you are going to have xy plus 1 all upon x 2xy minus 1 dx plus then 2 minus xy all upon y 2xy minus 1 dy is equal to 0. Now, see, after multiplying by the integrating factor, as I told you, the integrating factor, it is like the factor that we multiply to this non-exact differential equation to reduce this non-exact differential equation into a exact differential equation. Now, from here, I can say that this, okay, this differential equation is now exact. Okay, is now exact. If you want to check, just make this one as your m1 and here as your n1, then find the derivative of this n1 with respect to x, and find the derivative of this m1 with respect to y. These will be equal. Okay? So now that they are exact, okay, now that they are exact, so what should we apply, or how should we solve? We should apply now the integration of xy, okay, xy plus 1 all upon x 2xy minus 1 dx plus, now integration here of 2 minus x y all upon y and 2xy minus 1 dy must be equal to c. Now see, here y must be a constant number, and x terms for the second integration must be excluded. Okay, excluded. Nice. So see, can I exclude here all of them? I can't, because here if I apply partial sum, I will have a function of y only when I split this one as a partial sum, when I start to solving for dy, okay? And here also we will apply partial sum to solve this integration, okay? Because here we have a product here in the denominator, so we can apply partial sum with respect to x, okay? Here, partial sum with respect to y. So how to solve this one? That's the question. So here, the partial sum will be given as a upon x plus b upon 2xy minus 1. Okay? This is dx plus integration of a upon y plus b upon 2xy minus 1. Then dy. Okay? Do not forget this x terms. Okay, x terms excluded. Okay, excluded. And here y constant. That's the point. See, when y is constant, here y is constant, and here x terms are excluded. What does it mean? That's the question. When I have here, do I have an x term? No. So here I have an x term. If I have x term here in this expression, it means that this guy must be excluded directly. So this will be equal to 0. No need for calculus. No more. Okay? Now, what do I do to find this expression here? Okay? What do I do to find what will be the a here? I will start for a. To find a, just do this one. Y equal to 0. Okay? I will find this a. If y is equal to 0, just make this term equal to 0. I will come here, 2 minus xy all upon 2xy minus 1. I will not forget the term, I will not put here the term that is being, the term that I'm doing it equal to 0. I will not put this one. So, okay, and I will come here for y equal to 0. Put here y equal to 0, this will be 0. And put here also, this will be 0. So here you get that a will be equal to 2 upon minus 2. Okay, this is 2 upon minus 1. 2 upon minus 1, it will be minus 2. Okay, from here you have your a directly. Okay, yes, you have your a directly. And it's done. Now, let's go to find this expression here beside. Okay? No need to find b, because b is a term of x, so x I will exclude 0. Now here, make it 0. Then come here, take this y, that is 0, out. Then make it y0, y0. 2 upon minus 1, minus 2. It is your a. It means that here I will have the integration of minus 2 upon y. Now, let us solve for this one, for this second one. For the second one, what do we have to do? That's the question. That's the point. Okay, for the second one, as I was saying, so what should we do in this case? Okay, we can also just from here, we know what is a directly if you apply the same method. But here you are open, okay, you can apply directly this method, or you can also, and this one I will solve with another method, okay, so that you can see that you have various ways to solve this one. Okay, whenever you feel like you are in doubt or you are something like that, it sounds like tricky, so go for this one. See, suppose, okay, you have this one. This is a, okay, you want to find what is a here. To find what is a here, make this x equal to 0. X as a subject equal to 0. You will come here, okay, and put here 0. So a will be equal to xy plus 1 upon this x will be excluded because it is the one that is 0. It will be 2xy minus 1. And here make for x equal to 0. For x is equal to 0, what will be here? 0. And here also 0. You'll be 1 upon minus 1. So a will be 1 upon minus 1. This will be minus 1. It means that here a is minus 1. So how to find for this b? Okay? To find for b, okay, how to find b, this guy. So to find b, here what you have to do, you have only to find here, see, here how many, so as we are solving for x, okay, forget about this x, okay, we are solving for x, so x is our variable, y is a constant. So to find b, this b here, the only thing we have to do is, how many y do we have here? y1, 1y, and 2y. So this 1 plus 2. How many do you get? This will be 3y, just like this. And b will be equal to 3y directly. Okay? Even here, if you wanted to find what is b, you should just come here. Here you have like you are solving, okay, for y. So forget about your y. You get 1x here, and here you get 2x. This times this, or this plus this plus this. Forget about the sign, just sum this and this. You get 3x. So there, your b should be 3x. Okay? And if you are in doubt, you can just go and just find these equations as it is. Just come here and let us, for suppose I will solve for this one, applying partial sum, this one. And let us see whether we are going to have the same result here. You have xy plus 1 upon x, then 2xy minus 1. And here I'm considering x as variable, okay? If x is my only variable, it means that all of them must be constant. Y is constant, 2 is constant, and everything is constant. Unless, except this x. Let us solve for them. Okay, let them solve. So you get this a is equal to a upon x plus b upon 2xy minus 1. Then just solve this one. This come here, this come here. You are going to have like, okay, you are going to have 2, okay, 2ya multiplied by x, this time this, and this by this, minus a. And this time this one, plus bx, all upon the same, 2xy minus 1. And here, the same and the same. Okay, x, 2xy minus 1. Okay, forget about this. We will just make this part here up equal. Okay? So see here, what do we have to do? The terms in x, okay, x is our variable. The terms in x must be together. So I will make it equal to xy. Okay, so x is equal to x, y will be equal to the coefficient of x over here. And the term that is alone will be our a. Now see what you are going to have. This x and this x, okay, let me just erase a bit of here. Need some space here. See, what we have here, we will have like x, y plus 1 is equal to this x can come together. So 2y a plus b times x minus a. Okay? Then put it all together. This term in x and this term in x. This is the coefficient of x. This is the coefficient of x. So this must be equal. Y must be equal to 2y a plus b. Then 1 must be equal to minus a. So minus a is equal to 1. See, just by seeing this, you will directly understand that this will be the same as that one. Okay? So come here. And what you are going to see here, so if a is equal to minus 1, it implies that a is equal to minus 1. Okay? That's the same that we got. A is equal to minus 1. Substitute a is equal to minus 1 here. It will be minus 2a. So b will be equal to minus 2a. When it come here, plus 2a. So b will be b minus 2y is equal to y. So b will be equal to 3y. This is your b. Okay? So if you don't want to go in this way, you can go in this way. Just considering x as a variable, then solve for x, put together your x, and you'll get the points. The same will happen here. Okay? If you don't want to go to this way, just solve for y and consider x as a constant. You will get the same solution. Okay, now let us solve. Okay, let me solve this one. Okay, so as I do not have too much space here, I will solve here up. Now see, you have this one is minus 1, so this integration, instead of a, I will put the value of a, it is minus 1, so it will be minus 1 upon x plus, then instead of b, we know b is 3y upon 2xy minus 1. This is dx, okay, where y is constant. And here plus integration, the same. Here, we don't need the term in b because here we have x, so we have to exclude. We will need just this term here. What is a? A is equal to minus 2. So it will be minus 2 upon y, dy. Okay, x terms excluded equal to c. Now what you're going to have here, this one will be minus ln of x, and this one, I know that this guy is a constant, okay? This will be plus, okay? See this integration here. When you derive this one, what you'll get? If you derive this one with respect to x, you are going to have 2y, right? So I have to put 2 and I have to take 2y, okay? Just like this. This y can stay there, then I will have this one. This will be 3 by 2 only. Yeah, 3 by 2. And y can stay there. Stay by 2. ln of 2xy minus 1. Okay, then plus, okay, if you just apply derivative to this guy with respect to x, what will you get? 2y upon the same. So 2 and 2 will be cancelled out. This one will be minus ln minus 2 ln y. And that is equal to c. Now see this expression over here. Okay? This expression, you can just put these two together. Minus ln of x times y squared. Okay? Times y squared. And this is all negative. Plus 3 by 2. 2xy minus 1 equal to c. Now see, this and this. Okay? Hey, sorry, this is ln. And this can come here. ln of 2xy minus 1, 3 by 2. Okay? This is ln, this is ln. You can just make it as ln of 2xy minus 1 all upon 3 by 2 divided, okay, divided by xy squared is equal to ln of c. This is a constant, so ln of c, it's the same. So what will it be? This will be ln. So you can forget about ln. This will be 2xy minus 1 raised to 3 by 2. And here it is like x squared y equal to c. Okay? Here you can forget this one. So, and yeah, in this way you have the solution for this exercise. Okay? Now let's go for another one. Okay? Now suppose we have a differential equation like this. So how to solve this? That's the point. Okay? How to solve this differential equation? So here you can apply like the same m, consider m and n, and solve this one. Okay? It's up on you. Okay? It's up on you. So here you can apply also the concept of linear differential equation. As I can see here, I have y log y, and here I have x and log y. So I can just make it as a differential equation with respect to y. With respect to y, like of x. X must be my dependent variable, so y will be my independent variable. Why? Because here x is linear, and differential of x is also linear. Then I can solve this one. Okay? The other method is to, like, if you consider m dx plus n dy, just try to solve it, okay? Find whether this differential equation will be, how can I say, will be exact or non-exact. Like find del m, del y will be this one. If you derive this guy, it will be 1 like log of y plus y times 1 upon y. So it will be 1. Okay? Then, if you find del n, del x, what will it be? It will be only 1. Okay? Now, if you see this way, okay, here, if I suppose make one like this, okay, if I find differentiation of this minus this minus this, what should it be? Just try. It will be 1 minus log of y, okay, plus 1. Just like this. Then divide it by m. What is m? Y log y. See whether this function will be a function of y only. Just see whether this function will or not be, okay? How much will it be? It will be 1 minus log of y minus 1. This and this will be cancelled out. So y log y will be a function of y only, okay? Because what did I did here? I did del n, del x minus del m, del y divided by m. And this must be a function of fy. This is what I did. So this one, log and log will be cancelled. So it will be minus 1 upon y. That is a function of y. If this is a function of y, what will it be then? What will be the, how can I say? What will be our integrating factor for this case? Okay? When this condition, first and second, this is equal to this, so if here, in this case, will be Euler, okay, integration of f of y dy. So if, as we know, will be the value that will be multiplying all of this, then it will be a exact differential equation I can solve, okay? We know that this is non-exact because this is different from this, so that's why I just decided solving in this way, okay? That's why I solved in this way, because it is non-exact differential equation, okay? Yeah, and I see, if I take this minus this will be only a function of y. Then divided by m, it will be only a function of y. So that's why I wrote something like this, okay? This is like 1 minus log of y plus 1 all upon y log y. And this I got 1 upon y only. This is a function of y only, right? Then find what will be your integrating factor. So if will be Euler integration of I of this guy. This will be minus 1 upon y. That is f of y. dy. So Euler of this guy, this will be minus ln of y. And this will be Euler ln of y minus 1. This will be 1 upon y. This is the integrating factor. Now that you found the integrating factor, multiply by all of them, okay? 1 by y by this. It will be y log of y dx time 1 by y plus x minus log of y, okay, dy equal to 0 time 1 by y. So just solve. You are going to have log of y dx plus this and this will be x by y minus log of y divided by y, okay, and here dy equal to 0. Now that I multiply by integrating factor, what should I write here? Now it is exact differential equation, okay, because it was not exact, non-exact differential equation. Now that it is exact differential equation, what should you do? You should just apply integration here and integration here. Here, y is constant, and here x, you have to exclude. Okay? Exclude all the terms in x. So here, this one will be 0. There is x in. And here, y is constant. This guy come out. It will be log of y, integration dx, plus here it will be negative log of y upon y dy equal to 0. Sorry, okay? After integrating, it is c. Okay, c. Now c. This one will be log of y, okay, time x, okay, minus this one. We know that log of y, if you derive, suppose you have log of y, if you derive, will be 1 upon y, right? So it means that I have here 1 upon y, 1 upon y, 1 upon y. It is the derivative of log of y. So we can write in this way. So it will be log of y d log of y2 is equal to c. Now this will be x log of y minus this is log of y d log of y. It will be log square of y upon 2 equal to c. Nice? So this will be our solution. Okay? This will be our solution. Now I will solve the same exercise, okay? The same exercise by applying linear differential equation. Okay? The same exercise by applying linear differential equation. Now see, if I apply linear differential equation, I said this is the derivative, how can I say, like differentiation of x is linear, and x here is linear also. So we have to order this guy with respect to x. Let us try. So how will it be? This guy must come out of here, and this guy must come out of here and come here. So I will divide this dy, y by log y, okay? Y by log y, just like this. Y by log y, then dy, okay? Then here I will do the same. Y log y dy, okay? Just like this. So this y log y will be cancelled out, and here dy, dy, then this will remain the same. So dx dy plus, okay, this divided by this will be x upon y log y, then minus this and this log y upon y log y equal to 0. Now see, this and this will be cancelled out. Minus 1, this guy can go there because there is only terms of y, and this is dx by dy, x, and you can go there. So dx dy plus, okay, 1 upon y log y times x equal to 1 upon y. Okay, this is in a linear form. Now that you have this one, this is your p, this is your key. Okay, your q of y is this, and your p of y is this. Now let us solve this equation. So here you got what? First, what is the integrating factor? Integrating factor, it is Euler of integration of p of y dy. Okay, so this will be Euler integration of this one. 1 upon y, then log y. Okay, this is dy. What will be this integration then? Okay, it looks like very difficult, but see, 1 upon y, this is derivative of this guy. So I can write in this way. Okay, this is log of y. Okay, just let me see this one. This will be log of y. Okay, log of y raised to minus 1. Okay, then differentiation of log of y too. Then just apply derivative in here. What will you get this? Here it will be, this is minus y, right? So minus 1, it will be Euler, okay, ln of y. Okay, this is the same as I wrote something like this, 1 upon log of y. Okay? Here we have derivative of y, of log y above, and derivative of log y down. So this will be ln of ln y. And so here, our IF will be equal to ln of y. This is your IF. Now, you make this one in dependent variable, the solution, okay, given solution. Here, the given solution is, what will be the given solution? Dependent variable x, dependent variable, time IF is equal to integration of IF time q dy. Now, just solve this one. Okay, just solve this one. What is x? It is x. IF, it is ln of y. Here, integration of ln of y time 1 by y, and this dy. So it will be x time ln of y. And here, what will you be? What will you get? This is ln of y time, here, again, ln of y derivative. So, the ln of y. You see, what you're going to have, plus c, you can just add here, plus c, this will be x ln of y, and here, again, it will be ln square of y by 2 plus c. Check if they will be not the same. They will be equal. Okay? Check the solution that I got here and check the other one that I got in there. Okay? So it's up on you. The method that you're going to solve, it's up on you. Okay? Yeah. But till there, it's okay. Let us jump for another exercise. Okay. Now, suppose we have this one. This is the next exercise. Okay. So for this exercise, okay, you can try. You can try other methods, okay, like it is in this way, so you can see whether you can solve in any other method. So like we can just split this one as a Euler raised to x by 2, or 2x plus y square, and this is y cubed dx. Okay, you can split in this way, then find this m and find this n. But the point is, whenever you start solving by this way, this will be your m and this will be your n. If you try to solve this one. So see, here separable method cannot work out. Here it's not homogeneous. So it's not in a function of f of x, y, and so on. No way. It is not also. Now what you have to do, let us see whether this, okay, whether this is exact or non-exact. But I know that for those cases will not work out. Now del m and del y. See, del n and del m and so on. If you solve this one with respect to x, you are going to have 2 Euler raised to 2x. And if you solve this with respect to y, you are going to have 3y squared. Now see, if you try to do this minus this and check if I divide by this or by this, it will not be a function of x only or of y only. Forget about. So this case is particularly a very tricky case, okay? And I guess this is coming from GTU, okay? And for this one, you'd better try, okay? You'd better try, because for this one, exact and non-exact are not working out. So you better try linear differential equation, okay? So for linear differential equation, how will it be? So this time here, this will be Euler 2x plus y squared, and here dy is equal to y cubed dx. Now see, this is y cubed dx. Nice? This is dy. If I try to solve, okay, if you see this one, y squared, y cubed, then if I try to solve, okay, with respect to y, it will be a little bit complicated because, okay, because here, if I'm applying linear differential equation, I have to make it like a function of dy dx plus px y equal to q of x, and dy by dx plus, dx dy plus p of y time x equal to q of y. Okay? Then we know that sometimes we have here x raised to n or y raised to n. That is Bernoulli's equation. Okay? These are also kind of linear differential equation because this can be reduced to a linear differential equation. So see, this one, can I do or can I transform this one in this? Impossible. Okay, there will be no term in y and x. So we have to try the reverse form. So here I have just to come and here dy and here also by dy. Okay, so this can cancel out. Actually, I do not cancel out. Okay, yeah, what I do is just I differentiate. Okay, it's not a kind of cancellation. Suppose we have dy here, right? So what I do here, I will just come here, okay, and come here too. I will make this function as like d of dy. Okay, yeah, just kind of, okay, not like, this has not like, in a way, it's not like in a way of cancel, okay? But anyway, maybe in another video, I will just try to explain what happened here directly. So dy, and here dy. I just changed the order. This is will be cancelled out, but this is not cancellation actually. This is like whenever you are having like opposite effect, okay? This is dy and this is dy also. This is y with respect to y, this is this. So it's like opposite effect, okay? Like you had something like d, this is y out, and this is d with respect to y. This will be 1, okay? Yeah. So it will be Euler raised to 2x plus y squared is equal to y cubed dx dy. Okay? Now see, this expression is like this, okay? This looks like this. So this y have to go outside of here, okay? Because it must look like this, okay? Or like this, okay? Just in this way. Now see, if it looks like this, what will I take? So this one, y by cube, and y by cube. What will I get? This expression here, it will be dx dy, okay, equal to Euler 2x by y cube plus 1 by y. Now see, you have Euler raised to 2x, okay, and here I need an expression, okay, like x, and here I need an expression also of this one. Now see, this expression or this equation doesn't look like a linear, okay, in a linear form, but it can be reducible to a linear form, okay, applying Bernoulli's second type of equation, like f of x dash is equal to dx dy plus p of y, then f of x equal to q of x. Q of y. Okay? This can be reducible in this way. How? This, take out this guy and divide it by all. You're going to have this one, Euler 2x dx by dy. And here also 1 by y cubed plus the same, okay? You can just write it like this one, y and Euler minus 2x. Here also, Euler minus 2x. Okay? Now send this guy here. You're going to have Euler minus 2x dx dy minus 1 by y, Euler minus 2x is equal to 1 by y cubed. Now in this way, it is in Bernoulli's form. Okay? Why it is in Bernoulli's form? Because if I derive this expression here, will be the same as this guy. Okay? Now we have to do u is equal to Euler. I will call v. Call me Mr. V, okay? V. So v is equal to minus 2x. Then what should I do? I should derive this v with respect to x. Now see, many people got confused. Not x, y. Many people got confused. How come I will derive this with respect to y? Why y? That's the point. See, here x is a function of y. Okay, if x is a function of y, so it means that x is a function of y. Whatever function that I add here, as I suppose, suppose I do a supposition like this one, I do a suggestion like x, okay, a term of x, okay, must be equal to u. This u will be also a function of y, because it will be like, you can apply this chain rule. If x is a function of y, and if x is a function of y, okay, x is a function of y, and this, from this x, I have another function that is u, so what does it mean? That's the question. Like, suppose I have the one and u. If x is a function of y, and x is equal to u, okay, is equal to u, so directly this u will be a function of y too. This u must be a function of y. So that's why I write this one, okay? V is a function of dy. And then I will derive this expression will be minus 2 Euler minus 2x, then dx dy. Okay? Now see, minus 2 can come here. I will get minus 1 by 2, and here also minus 1 by 2. What will I get? I got this guy. Okay? Just pick up this expression, and the one that I'm going to write here. What will I get? This minus 1, so minus 1 by 2 dv upon dx is equal to Euler minus 2x dx by dy. Okay? This is the expression that you are going to put over there. Okay, now substitute this and this in there. What should you get in this expression here? What should you get? You get this one. This is equal to this. And this v is equal to this. Substitute, you're going to have minus 1 by 2 dv by dx minus, okay, 1 upon y, v equal to 1 upon y cubed. Now just solve this equation, okay? How to solve, that's the point. How to solve, that's the point. So multiply, this guy must be like there, dv dx only. This one must get out. Then I will multiply this by minus 2, and here minus 2 also. What will it be? Minus 2 will be dv dx, then plus 2y v is equal to minus 2y cubed. This one is my p of y. This is my q of y. So now it is linear. Okay? Now it's not anymore Bernoulli's, now it is linear. Linear differential equation. So if it is linear differential equation, what does it mean? It means that now I will have this one. What is v? If will be equal to integration of this guy, py dy. So integration of py dy. Py dy is 2 upon y dy. This is Euler raised to ln of y squared. And this will be y squared. Now that you find what is if, so the solution will be if time the independent variable that is my v, it's equal to if time q time dy. Okay? Plus c. Now, if is y squared. What is v? V is v. Integration, this will be if y squared time, here it is 1 upon y cubed, minus 2 y cubed, and here dy, plus c. Now solve this equation, okay? I will solve here up, because I'm running out of space, so I'll solve here up. So see, this will be y squared times v, okay? Y squared times v is equal to this integration. And see this one, y cubed, and this one will be cancelled out. You are going to have only minus 2 out dy upon y plus c. Then y squared. What is v? We know that v is Euler minus 2x. So Euler minus 2x is equal to minus 2. And here, this integration is ln of y plus c. This will be our solution for this exercise. Okay? I hope you may enjoy this. Okay? It's a very good exercise. I enjoyed doing this one. So a very good friend of mine just he suggested me this exercise, and I solved, and I found this very important and very good exercise to be done. Okay? Yeah, and the last but not the least, I will just quickly solve this exercise. So, see, this exercise here, to solve this exercise, the first thing you have to do, or you have to understand is, okay, here x and y are argument, x and y are argument. So whenever you have this xy here and xy here, okay, it indicates you, so you can just solve this guy by applying variable. It means that this is reducible to a variable, like a separable variable method, okay? Yeah, but you have to make some assumption or some supposition, you have to suppose that x plus y, because x plus y is common here. So x plus y equal to u, suppose, okay, to solve this one. Otherwise, if you try any method, it will be a little bit complicated, because when you try to find whether this will be homogeneous or not, and actually, if you look closely, yeah, it's not homogeneous, So none of these methods will work out, okay? Then try on other methods, okay? But here, the clue here is that x plus y are common. So we make this one equal to u. So that then we can apply this method of separable methods, okay? So x plus y equal to u. When you make this one, then find the derivative with respect to x, okay? You can find with respect to x, okay? Or you can do with respect to y. It's up on you. But I will do with respect to x, because x here is the one that is concentrating the less part of this function, just like this. So we'll do with respect to x. So this will be d of x plus y, okay, dx, and here du by dx. Now, what will it be? It will be something like 1 plus dy by dx. It's equal to du by dx. Then I will send this guy right there. So it implies that I will get dy by dx is equal to du by dx minus 1. Okay? Now that we are done with this, what is the next step? We will substitute this one in there. Okay? Let us substitute. So it means that I will organize with respect to y. Okay? Here dx go out, so then here will be dx. Nice? So yeah, this one will be out. So we will get something like, if we substitute, we'll get sinus of u minus 1. Okay, sine of u minus 1 plus cos of u dy, not dy. dy dx is what? Du dx minus 1 equal to 0. Now here, what we will do, sine of u minus 1, and here we will just make this distribution plus cos of u du dx minus cos of u is equal to 0. So what will be the next step here? See, the next step here is just to put all of this term out there. So this will be cos of u du dx is equal to cos of u positive. Then these two guys go out, it will be minus sine of u and plus 1. Nice. Now from here, this cos here go down. Okay, this cos here can go down. Okay, can go down. Just this will be du dx is equal to cos of u minus sine of u plus 1 all upon cos of u. Okay, so here we will do the cross sign. Okay, what will it be? It will be what? Cos of u du. I have to put together u with du. U, okay, function of u with the differentiation of u. All upon cos of u minus sinus of u minus 1. Okay, equal to dx. Just like this. Now, I will integrate both sides. Okay, because it's a separable method. Then here, this integration. What is this integration? That's the point. Here plus c. What is this integration? Now, to find out this integration over there, that integration over there, you have to understand a very basic principle of trigonometry. So whenever we have a function like this, cos of u, and this one, we have to make sinus of u, then cos of u. We have to make a substitution like this. Tan of u by 2, tan of, in this case will be u by 2 is equal to t. The general substitution. Whenever you have cos of u, then down you have this expression. This is the general substitution that you are going to make. Okay? Yeah, this is the general substitution you are going to make. So, yeah, this will be the general substitution. You can go by this and solve this exercise. Okay? Yes. As I was telling you, okay, here you can do this supposition, you can do this this transformation, and here you will have this like 2t upon 1 plus t squared. Okay, it's like here tan of u by 2 must be equal to t. Then you will do this transformation. We know that sinus of u will be equal to 2 sinus of u by 2 cos u by 2. Okay, all upon 1 plus, all upon this, okay? This is true, right? Then I come here and I multiply by sec square of u by 2. And I divide by sec square of u by 2. What will it be? It will be 2 sinus u by 2 cos u by 2 divided by, what is sec square? Sec square is 1 upon cos square u by 2. All divided by, what is sec square? We know that if we make this one, sin x cos square equal to 1, we divide by cos square. This will be cos square, this will be 1, and this will be tangent. Tan of x square plus 1, and here it will be sec square of x. We know, then it will be 1 plus tan square of u by 2. Here you are just to cancel out this cos and this one. You are going to have 2 tan of u by 2 divided by 1 plus tan of u by 2 square. Okay, it means that sinus of u with respect, as a function of tangent, it will be 2t upon 1 plus t squared. If you do the same process, okay, the same process with cosinus, cosinus of u is equal to cosinus of u by 2 plus u by 2. Okay, the same you can apply for this one, and it will be cos square of u by 2 minus sinus square of u by 2. Now come here and multiply by sec square of u by 2 and divide it all by sec square of u by 2. What will it be? It will be, okay, cos square u by 2 minus sinus square u by 2, okay, u by 2 divided by cos square u by 2, all divided by 1 plus tan square of u by 2. So this and this will be cancelled out. You are going to have this and this will be 1, and this will be tan square of u by 2 divided by 1 plus tan square of u by 2. So it means that cos of u is equal to 1 minus t square upon 1 plus t square. You see this? Okay? Yeah, you can go under this transformation and solve this guy. Just if tan of u by 2 is equal to t, so then solve them. Where you find u, put 2t divided by 1 plus t square, and where you find cos, you put this one. Then what should be my derivative, differentiation of this guy? See, this one, if you want to differentiate, then come here, then apply tan inverse of tan of u by 2 will be equal to tan inverse of t. So what will it be? It will be tan inverse of t equal to u by 2. These 2 can go there, 2 here, it's fine. Then apply derivative. What you get? Du, okay? You got du. Sorry, this constant can stay here, can remain, it's no problem. When you apply derivative, it will be du by 2 will be equal to tan inverse derivative of this guy. Okay, I will derive this guy. What will it be? It will be dt all upon 1 plus t square. Okay, that's the point. Dt is all upon 1 plus t square. So these 2 can go. Okay, these 2 go. These u must leave. Yeah, these 2 must leave. Okay, it's okay. 2. Nice. It means that where I find du, I will put this expression. So if you put this and put this and put over there, you will solve this equation. But you know what? This is the general way. Okay, this is the general substitution. But there are some very easy ways to solve this one. Okay, and this is the way that I'm going to solve right now. Okay, because okay, so when you don't know that much, you can go in this way and you can just solve, and that is fine. But because of the time, I will just go in this way that I'm writing right there. So see, here you have this expression, right? So differentiation of cos of u. So what I will try to do is just to make this guy as a different square, differences of square, okay? So to make it a differences of square, I will multiply this one, this expression, okay, by its pair, like conjugated, okay, by its conjugated. What should I do? What should be the conjugated of this one? It is cos of u minus sinus of u, okay, minus 1. Its conjugated should be cos of u minus sinus of u, okay, plus 1. Okay, this should be its conjugated. Now I will multiply by then. So it will be cos of u minus sinus of u plus 1. Okay, plus 1 divided by, when I multiply this and this, when I multiply a number like this expression with its conjugate, what will it be if I multiply this and this? Okay, it will be cos u minus sinus of u square minus 1 also square. Right? It will be this, surely. Okay, this is du, and this is integration of dx plus c. It will be this, surely. It will be this. Okay? So it's like when I multiply a plus b times a minus b. It will be a square plus b square. Okay? Minus b square. then it will be the same here, like cos of u minus sinus of u square minus 1 square. Okay, now see, this expression here, what is this equal to? This expression is equal to, see, I will put here down, cos u minus sinus u. If I put it square, what will it be? Cos square u plus sinus square u, then minus 2 sinus u and cos of u. Okay, this one will be 1 minus this expression here, it is sinus of 2u. So it will be this one. 1 minus sinus 2u. It will be 1 minus sinus of 2u minus 1. And here, this and this will be cos square of u. This and this will be minus cos u and sinus u. And this will be the same, plus cos of u du. And here we know this is x plus c. Okay? This is x plus c. Just the question. Okay? Let me erase this. Okay. Now see where comes the magic. Okay? The magic come here. So it means that I will get 1 minus 1, it is 0. So minus sinus of 2u. And this will be this. Okay? Just like this. This will be cos square of u minus cos u sinus of u plus cos of u. Okay? This is du is equal to x plus c. Now check. This expression here, that we have here, it is equal to what? This one is equal to, I would separate each integration like cos square of u upon this guy. This is 2 sinus u cos u. This is the same. And and here du. Then minus integration of cos u sinus u all upon sinus u to sinus u and cos u du plus integration of cos u and here to sin u and cos of u du. This must be equal to x plus c. Very good. So just simplify this and this. Simplify this and this and this and this. This and this. Okay? See what you're going to have here. This will be integration of 1 by 2. And here I will get cotangent, cot of u du minus integration here. This will be only 1 by 2 du plus another integration here. This will be 1 by 2. And this will be cosec of u du equal to x plus c. Just like this. So here, to finish, it will be 1 by 2 ln of cotangent. This will be sinus of u minus 1 by 2 u, then plus 1 by 2 cosec u. Cosec is ln of tan, okay, of u by 2 equal to x plus c. Nice. Okay. Now that we just got these expressions, this is the solution, nice? We have to go back to our substitution. We said that x plus y is equal to u. So where you find x plus y there, put u. Okay? Just put u. And you are done. Okay? Let me see. Okay, I will write just the final answer. Okay, just the final answer. Again, I ain't got no more space here. I have to find space over there. So See here, I will do something like 1 by 2 ln of sinus of u. See, sine of u, you have here sine of u, and here you have this also. So you can multiply, okay? Tan of u by 2. Why I'm multiplying? Because it is like 1 by 2 ln of sine of u, and 1 by 2 tan of u upon 2. Then minus 1 by 2 u is equal to x plus c. This expression here, we know sinus, okay, sine of u will be equal to 2 sinus u by 2 cos u by 2. Okay? Then just do some basic simplification. Like 2 sinus u by 2 time cos u by 2 time, here it is sinus u by 2 upon cos u by 2. Okay, this is your tangent, this is your sinus of u. So this and this can be cancelled out. Minus 1 by 2 u x plus c. So this will be 1 minus 1 by 2 ln, okay, ln of what? This and this will be 2 sinus square of u by 2 minus 1 by 2 u equal to x plus c. Now you can just put what is your u there, okay? U is equal to x plus y. So will be 1 by 2 ln of 2 sinus square of x plus y upon 2, okay, minus 1 by 2 x plus y is equal to x plus c. Okay, this is the solution for this differential equation. Okay, this is the solution for this differential equation. I hope you may enjoy this one. Thank you. See you in the next video that will be about higher order differential equation. Okay, bye guys.